Okay, so this is a little demo. It's just kind of off the cuff. Some of you are asking me questions about what you need to write in your essay, and so I thought I'd kind of just summarize the things we did in class. So first of all, rather than using a calculator, because if you use a calculator, let's say, and you just say something like 1 divided by 13, it is not very helpful. This is actually quite a pathetic response that your calculator is giving you. Okay, so if you go into Wolfram and do the same thing, it takes less effort because you've got a keyboard, and then you get a full done out answer, and it tells you right away this thing has a period of 6. Now you notice something Wolfram does for you. If you start with a 0, it doesn't start your repeating decimal sequence on a 0. It starts at the first non-zero digit, and then it draws the bar to extend over the 0. Okay, so that's useful. So the first thing we started with in class when we were talking about this was 1 over 7. And so what we found out is that 1 over 7 looks like 142857. Okay, so 142857, and let's put a bar over that. Okay, this was 1 over 7. Okay, then what happened for 2 over 7? We found out that we were actually using the same digits, but we started at the number 2. Okay, and so we found out that this was 0.285714. Okay, great. And so then what we ended up finding out was that if we continue this logic, we had 3 over 7, 4 over 7, and I'm actually going to erase this for a second, point out some other things. 4 over 7, 5 over 7, and 6 over 7, right? And all we have to do is take all these possible cycles and put them in the right order. So let me do it this way. Since I have a computer, I can do some things that you can't do, right? I can say 0.142857. First of all, I'm going to erase all this stuff. Well, I guess I'm going to erase it this way. All right, 142857 is one sequence, and maybe the next sequence is going to start on 4, 428571. But wait a minute, you say, we're skipping. Yeah, sure, why not? I'm just going to generate all the sequences that are possible, and then I'll just put them in the right order. How's that? Just going to go ahead and generate all the possibilities and not worry about what order they're in, because then I'll just paste them in the right order. So I just put them in ascending order, because if these are all the possible repeating decimals and I have all the possible fractions, they have to go in order. And why did I write the second half of the fractions backwards, like in reverse order? Is because I wanted to show you that 1/7 plus 6/7 equals 1, and that's a string of 9. So for example, this digit here, this 1 and this 8, they have to add up to 9. This 4 and this 5, they have to add up to 9, and so on and so forth. For every set of fractions where the two fractions add up to 1, then the digits have to have the same length, and they have to add up to 9s. Okay, so that's kind of cool. All right. Okay, so let me try to delete this stuff because it looks kind of messy. Okay, so let's go back to playing on Wolfram and try to get some more insight here about what's going on. What about if we put as a denominator 8? Or, that's boring. 2 over 25. Well, that's boring too. We actually know what's going to happen to that. That's a 0.08, no big deal. Okay, What about 7 over 625? Yeah, that's got to be exciting, right? But it's not exciting. Why is it not exciting? Well, it's irreducible. Okay, that means at least it's already in lowest terms. But it has a terminating decimal. What does it mean for a decimal to be terminating? Well, it means that all these digits are missing, like they're all zeros. Why does it terminate? Okay, so 7 over, what was it? 7 over 625? Okay, so let's just do out long division and figure out what's going on. 7, 625. So how many times does 625 go into 7? That's ridiculous. Alright, it doesn't go into anything until this digit, so you just go ahead and start doing your subtraction. And then you get another 1, 625, I don't know. This is kind of boring. So we do this 750 minus 625. If I could do this, 750 minus 620. Why did I not get the 0 again? 750. What? 0 minus 625 equals 125. Yeah, I knew that. Alright, now what? I don't know, what did Wolfram say? The next digit has to be a 2. Okay. Next digit is going to be a 2. So, there. I think I'm just tired. But anyway, so what happened is it came out even. The remainder sequence looked like this. First we had like 7, and then like 70, and then 750, or like rather 75, I guess, and then 125, but then 0. So you see, we could have potentially had 624 digits before the thing repeated, but why does it not do that? Why does it terminate? Well, the secret is because 625 is actually a perfect power of 5, right? So did you know that? Okay, it's 5 to the power of 4, I think. Let me try this. Yep, 5 to the power of 4. So what happens is, in order to make this work out, you get 2 to the power of 4 in the numerator and the denominator. And what's 2 to the power of 4? Right? 2 to the power of 4 is equal to what? And then times 7 equals what? Is equal to 112 over a 1 followed by 4 zeros. Alright? So what that means from a practical standpoint is, here's your decimal, but then you have to move it over 4 times. 1, 2, 3, 4, and you end up like that. Okay, so that tells you what your number is. So anytime the denominator can be broken up into 2's, 2 to like the x times 5 to the y, x and y are integers, then you can just round up like we did here, where we brought in the extra powers of 2. You can do the same thing by bringing in the extra powers of 5 to bring everything up so that the denominator there is just a power of 10, in this case 10 to the 4th. Okay? And then you just take this numerator, write it down, but remember the decimal starts here, and then you just hop as many times as you need. It's the same as the number of zeros in the denominator. And so then you get this beautiful little situation where, okay, we've just given a technique for converting any fraction whose denominator is only factors of 5's and 2's. We have a technique for converting it into a terminal decimal. Okay, so hopefully that convinces you why that works. And then what? Okay, there's basically 3 categories. You either have something which I call an integer in disguise, which is something like, 14 over 7 is really just 2. It's not really a fraction. So that's a situation you can run into. Or you could run into something where you have like something like that. That's going to terminate because, again, it's 7 times something, and then it's going to be 10 to some power. It's going to be 8, right? You can adjust, you can figure out what you have to do to make this work out, but in the end, it's still going to be a terminating decimal. Okay. Now, the other category is the one you have to think mostly about, which is what happens when the denominator does not have just 2's and 3's. Something else which is not a 2 or a 3, okay, 13, something like that. What's going on is you have a set of remainders. So since this thing is not turning out even, you're not getting an integer, then when you start doing out your division, it can't come out even. If it could come out even, then you could reverse engineer the process we just talked about, and you could prove that the denominator only has 2's and 5's in it, okay? So you can't do that. So what's going to end up happening is you're going to keep going around in circles forever and ever and ever. But at least you're going around in circles, and not like an irrational number where the digits don't have any pattern. So you do this thing where you go like 4, blah, 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 divided by 13, right? And you look at the sequence of remainders. The remainder sequence starts out with 4, blah, 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 blah. The point is, eventually you have to run into 4 again, right? Well, maybe you don't. Maybe I'm lying to you. Okay? Well, think about it this way. What if you ran into the digit 7 at some point, and the digit 3, and the digit 10, and the remainder, rather. You run into those remainders. Eventually, maybe not 4, but eventually you have to recycle something. So just for the moment, pretend like maybe you don't have to recycle the remainder 4. But maybe your remainder sequence looks like this. 4, 1, 7, 8, 10, and somewhere down the road you've never used 4 again, but maybe you end up using 7 again. Well, then this would be a trap. Once you hit, anytime you reuse a remainder, it's going to bring you right back to that same remainder sequence again. Then it's going to bring you back to the same digit sequence, because the remainder sequence gives rise to the remainder sequence. Okay, so let's see how this turns out for 4 over 13. What happens here? Let's just go ahead and do one out. I'm going to pause this while I write this out. Okay, so here's what happened. We started off with 4 point as many zeros as you want. Okay, so 13 times 3 gives you 39. Here's your remainder. But remember, our first remainder was really 4. Then we actually had to pop in a 0 because our second remainder ended up being 10. And then we got the remainder 9, the remainder 12, and at the next stage we got the remainder 3, and aha, see, we got the remainder 4 again. But if you believe that long division works, you have no choice now but to continue this same sequence. You got to go 39, and then you get 10, and 100, and 9, and so on and so forth. So once you hit the first duplicate remainder, as soon as you duplicate that, you're predestined for all eternity to keep going around in that same cycle over and over and over again. Okay? So you notice we had 4, 1, 10, 9, 12, 3. That was the remainder sequence. So that means that's half of the remainders. We didn't do 2 or 5 or 6 or 7 or 8 or 11 or 12. 11. Yeah, so half of them we used. The other ones are in another family. Okay? But the important point here is I don't want you to worry at this stage of your thinking about this. What I want you to realize is that as soon as you recycle one, you're stuck in a loop forever. And so stuck forever. And the other thing you need to realize is that you have to recycle. Right? How do you know we have to recycle? Because we only have 12 possible candidates. So we have 12 possible remainders. So we could cycle after 12 or after 10 or after 6. Okay, actually that's not true. We don't have that many choices, but again, we're not going into that part of the discussion. Okay, so the only part I'm expecting you to understand is that you are stuck forever once you repeat a remainder, and that you do have to repeat a remainder. Okay, So understanding that is enough to get you through the essay, because what you want to do in the essay is explain why some digits repeat forever and ever and ever. Some fractions when expressed as decimals repeat forever and ever and ever, and some do not. And I think hopefully you have enough food for thought now to get you through that. And you have Wolfram.